we discussed the question of exit from an attractor. So this is, so the general title here is analysis of the Fokker-Planck of the non-selfadjoint Fokker-Planck equation. So this is just to remind you what we did last week. So I think the class is online, if I did correctly. Yeah, on air is on. So everything is online. But so what we said last week is basically how you study the problem when you have a stochastic dynamical system, which is x dot equal b over x. So this is what we have studied for the past 3 months. You have a deterministic drift, and you have the noise, which is of no small amplitude. So epsilon is small. This is some small Brownian motion. This is the noise. And here, what we discussed last week is the problem of escape from an attractor when the boundary of the domain is the limit cycle. Right? So if you go to, if you look at the past of this trajectory, the trajectory, when t goes to minus infinity, it converges toward this limit cycles. Right? So this is the limit cycle. Okay. And so what we were interested in last week, so this is a classical escape through a limit cycle. So what is the escape? Is that you have a trajectory which has some noise, which is attracted here, and then after some times you can, with a fluctuation, escape. Right? So this is the escape from the basin of attraction. Which we call omega, such that d omega is a limit cycle. And so what we said last week, so I'm not going to repeat, we looked at this situation when the attractor, so here this is the attractor where b, let's call it 0 equals 0, and this point, the point 0, is the focal point. This is the focus, which means that b, if we look at b and get some linearization, b of x can be written as b, a matrix multiplied by x, and the eigenvalue of b have complex non-zero part, right? So the eigenvalue of b is lambda 1, lambda 2, which are a plus ib, and this is a minus ib. A and b are real numbers. Okay, so last week we said that if you look at the problem of escape when the point here is inside, then what really characterizes the entire dynamic of escape is the time it takes to escape and the distribution of exit point. That is, there are two interesting quantities. So the quantity of interest, quantities of interest, there was the escape time, which is the mean time to escape condition that the particle started at position x, and there was a distribution of exit point. There are two things. So basically the time it takes to escape, and this has been calculated. This was calculated, this is in Markovsky, Schutz, 1980, I think 2, and 1983. This is in Science Journal of Applied Math. This is in Science Journal of Applied Math. And this is proportional to a constant C epsilon, which I have written last week, multiplied by a function by a constant u divided by epsilon. And then there is a formula for the distribution of exit points. So this was the starting point of last week's discussion, because we were interested actually not at this problem, but the problem where the attractor is located at a small distance from the boundary. This is what we said last week. And then we have the same picture, except that it occurs in this small distance between the attractor and the boundary can be of the order epsilon. Right? So this was the situation. So the same problem. This is the escape problem of escape from omega, which is again a basin of attraction, a single point, and the omega again has a limit cycle. The omega is a limit cycle. And so what we said last week is that, so I explained to you that when we did the simulation of this many years ago, this was not enough to have this for the characterization, because the distribution of exit time had peaks. So this is the probability that the time to exit equals t. And we have this distribution, right? So the time probability that when time is very large, is this converging to zero? But the question is where the oscillation were coming from. And of course, when the point is going inside, this oscillation disappeared, and we get something like this, which is a single exponential. So as the point is moving that direction, for example, when you're here, this is the distribution of exit time. And the decay, the exponential decay here, exponential minus lambda t. So the probability for t equal t when the point here is inside the domain, let's call it p inside. So this is the distribution of exit point. For t sufficiently large, is really a single exponential. And the lambda is exactly 1 over the mean first passage time tau, which is here. So this is the characterization. It's characterized fully this the long time asymptotics of this escape, because it takes time to escape. So basically, most of the information is in this distribution function, the tail of the distribution. So we asked last week, where are these coming from? So they are coming from, because when we express this probability distribution function, it can be expressed in terms of the eigenvalues. Right? So the probability, so if we look at the solution of the Fokker-Planck equation, all of this is still a summary of what we did last week. So the Fokker-Planck equation for this operator can be written dp dt. So let me remind you, you remember what is the solution of the Fokker-Planck equation, right? This is the probability to find the particle at position y plus dy, condition that x is 0, let's say equals x. This is ptx, pty and x, dy, and this, the density, satisfies the Fokker-Planck equation, which is dp dt. So in the case we're interested in here, this is epsilon Laplacian p minus divergence of bp. Right? And at time 0, p is 0 and x is delta Dirac, so at minus y, and on the boundary, p equals 0. P equals 0 on the boundary. So this is the Fokker-Planck equation. And now the distribution of exit time. So the distribution of exit time, this is exactly the derivative, or minus the derivative, of the integral of t, x, and y, and we integrate dx, and this, well, and if we have, and we can also actually, there is, yeah, okay. This is when we have a delta Dirac at y. Otherwise, here we integrate, and the y doesn't matter much. All right, so now if we extend, if pt of x can be formally expanded in eigenvalue and eigenfunction, which is exponential minus lambda kt, let's call uk vk, so this is x and y, where this is solution of the eigenvalue for the forward operator, and this for the backward operator, right? So the operator here is, I'll call it L of P. L is this operator, epsilon Laplacian minus divergence of BP, right? So L of U is solution of minus lambda k equals UK, and this is solution for the other one. Star. Star means the conjugated with when you integrate, you know, by part for the L2 be in this space. And this is minus lambda k vk. So you can always expand this, plug that in here. So if we integrate in x, so this doesn't touch much this, and when we differentiate this with respect to t, we just get a lambda k, which is a constant. So this can be really written as, I don't care really about y, but because you can always take a uniform distribution, it's unimportant. This is just to say that the initial point is at y, but if then we do simulation and analysis where you can average over a uniform distribution, y goes away. So this is the sum of really a constant exponential minus lambda kt. So if the operator is self-adjoint, but when b is the gradient of a function, all of the lambda k are real. So you have a sum of, and all of the lambda k here are positive, and this is a sequence which can be shown. Again, this is spectral analysis, and I'm not interested in giving a class on this, but basically you have the sequence of eigenvalues and going like this to infinity, and for you have a positive operator on a compact set. So you have a sequence, positive sequences, and there is no way you get any oscillations. So this is for the case where the operator, the Fokker-Planck equation, is self-adjoint. And when is it self-adjoint? For example, if B, when the field is a gradient of a function. For example, this is the case. If B is well, for example, a gradient or minus the gradient of a function phi. So this is a function, the gradient of a potential in physics. But if B has a limit cycle, this will never happen. Because the obstruction, the limit cycle, I mean, when we have a field that is sufficiently differentiable, this is, the limit cycle is exactly the obstruction, that the first obstruction you get for not having a gradient. Thus, the eigenvalues are not anymore real, but now, actually it can be proved that the first one, so now we are in the case where B is not a gradient, and actually it will never be a gradient, I mean globally, in the entire domain. And so it can be shown, and this, I'm not going to work on this, but lambda when the first one, this is the only real eigenvalue, which is positive. And the other one, and this is what we're going to see today, all the other eigenvalues are actually non-real. And they are complex eigenvalues. And now, if we want to understand this oscillatory effect, this is, you have actually similar effect in an entire field of physics, which is called the field of stochastic resonances, where now what you get here, you get the probability distribution of tau equals t. So can be written, the first one we said is going to be real, and positive. So we have a constant C1 exponential lambda 1t. But the second one is going to be then, it will have an imaginary part. And now, so this is the second term here. And now this term has to be rewritten. It's going to be exponential. So let's write it A t. You know, if I have here an imaginary part, it's equivalent to have a cosine. So this is like cosine omega t plus a phase and plus other terms. So now you start to understand. So, and then the second eigenvalue here is written A, or let's call it lambda 2, or lambda 2 tilde. So it's lambda 2 tilde plus I omega. So here the eigenvalue will be I plus minus, because you have the 2, so that you get something, you can use the 2 to have something real, because we want a real function, something that's. So what we get here, we get the first term, which characterizes the exponential part, and the second one, where you start to see why you have oscillation, because you have the cosine. And this tells you that if you want to understand something about this oscillation, you need to understand what is the second eigenvalue, and why the second eigenvalue, which is written here, why and how comes this term here is sufficiently close to that one, because if lambda 2 were very big compared to this one, this would be completely negligible. So it's not. So now you need to calculate. You need to make a calculation to see where and how this can be calculated and compared to the first one. That's why we need to calculate the spectrum. All right, this is motivation, why this is important. And if we get this, the distance between the peak, and this is something I said last week is important to calculate, will be given with respect to omega. So now, of course, the question is how the parameter lambda 1, lambda 2 tilde, W depends, how they depend on the field and the noise, so B and epsilon, and the initial parameter of the dynamical system. We have a dynamics, and we like to understand how they are related. Conversely, suppose you are making measurements, and you get this type of information about your curve. Now you can do a reverse engineering problem once we have those formula, will be to go back to the system and say something about your underlying dynamics that you probably do not know. So this allows you to do a reverse engineering.
Sorry, so the peaks should be periodic?
The peak should be, well, the peak should be periodic. Yeah. If we truncate here, if we add more term here, actually it is, and I will show, this is not clear a priori, but actually it's correct, because the eigenvalues, I'm going to show you that they are all proportional lambda nm. So this is, we're going to see that today, lambda nm, which are the eigenvalues here, can be written on the form n omega 1 plus m omega 2 I. So forget about this term, because this is going to be the exponential, but they're all proportional to the same frequency. So this is correct. Although, I agree with you, usually you don't care. Once you see some oscillation, you can truncate and already get this. Okay, so this is the motivation, and yes, last week I explained to you that we didn't come to this problem just by thinking and looking at the moon. It came out because of a problem in neuroscience that we found out that due to the parameter of the system to describe it, the focus was indeed very close to the boundary. Came out. This was the motivation. Okay, so now, all right, I'm not going to redo last week class, but I want, so this week, to discuss how do you find the spectrum of a non-self-adjoint operator? Where can you calculate? Where can you find the eigenvalue and eigenfunctions? And I will the short answer is that it's not trivial where it comes from. Let me explain. If you have a self-adjoint operator, what have you learned at school? That if you have a matrix, for example, the eigenvalue you obtain by just you diagonalize the matrix, if you can do it. This is for matrices. Now if you have an operator, like the Laplace operator, it's already one step higher. So for example, you have Laplacian u equals lambda u. You have the domain. So how do you find the lambda? The way to do it, like what people did 100 years ago, is to find the variational form. That is saying that the lambda is the minimum of the Dirichlet integral normalized by the L2 norm. This was for the first eigenvalue, and so if you could calculate this quantity, you could get access to lambda 1. And then lambda 2 is you do the same, but you are orthogonal not to lambda 1. And this is how you do it. This is the algorithm that is in the literature. Now what do you do when there is no variational form? Because variational form assumes symmetry. So the answer is that you have to analyze the equations. And what we said last week is that the way you analyze the equation is to use WKB. So when you have a non-self-adjoint operator, which is the case here, so you look for the solution of the eigenvalue problem of the form u epsilon equals k exponential minus psi divided by epsilon. And so last week, again, I'm not going to describe all of the detail, but psi is solution of what is called the Hamilton-Jacobi equation. And this is Laplace gradient psi plus b gradient psi equals 0. So this is what we did last week. So again, this is well known. And k epsilon is solution of the transport equation. So if you've never done that, you just take this equation and you plug it into the equation Lu equal, for example, minus lambda u, where L is the operator with epsilon. And to get this, you have to kill the term in one over epsilon, so that you group terms. And this is how we get this Eikonal equation, and then you get the transport equation. So now, still, how do you get information about the spectrum? So now this is what we're going to do now. It comes from the analysis of the transport equation in a boundary layer of the limit cycle. That's why it was so hard to find for 30 or even more years. So I'm going to show you, if you do a correct analysis in this boundary layer here, you can find an equation that you can solve. And the solution of this equation, it's like in quantum mechanics, when you do the quantification, when you come back, because in this neighborhood, if you find the solution, if you start at any point, due to the periodic properties, when you come back here, it has to be periodic. The same in quantum mechanics, when you do quantification, you go around, and this is how you get the quantification. This is the way. All right? Okay, so now we are ready for to start the class. Okay, so we will do this today, and then we will start narrow scale. Okay, so the goal of here is to derive, the goal of this, what we're doing now, derivation of the eigenvalue or the eigenvalue equation. So for this, I will go back to this domain, and we have to look at the property of the vector field on this limit cycle. So when we go close to the limit cycle, the drift B is exactly parallel to the tangent field. So B of x, I mean, if you write B as a function of rho, the distance, and S is the arc length, this is minus B0S rho normal. So we have, let's say this is a normal and a tangent. So this is a normal. Rho is the distance to the boundary of any point P here to the boundary d omega, plus B of S tangent. What does this mean? It means that when you are on the boundary, so we need basically here a local structure of the field in a small neighborhood of this of the boundary. So we can write this in the band here. For this is for rho between 0 and, let's say, eta. Eta is any positive number. So in this band, I assume that B can be written with a function B of S, which is strictly positive, and capital B of S, which are regular functions, strictly positive. So when rho equals 0, this is 0, and B is just proportional to the tangent. Okay. So last week, we wrote an equation. So we said that basically this, the transport equation, can be written, if I do this, all right, I will write here. You can erase here this part. So Q epsilon, K epsilon, I will now write it Q0, which is Q0, which depends on zeta and S. The zeta is the distance rho divided by square root epsilon. And so last week, what we wrote is we wrote that dq0 can be written as d psi squared minus zeta b0 of S plus 2 phi dq0 d zeta minus b of S dq0 ds. And so we said that if we have the first eigenvalues, or the mean first passage time, which is the same, this is equals to 0. So B0 and this are defined here. This is what I've just defined, this, and here this is the representation of the field. S is the parameterization of the limit cycle, so S, let's say, goes from 0 to capital S, where capital S, this is the period of the limit cycle. And phi satisfies some type of Bernoulli equation, which is phi squared plus B0, so this is phi of S, B0 of S, phi of S plus 1/2 of B of S, phi prime of S equals 0. And phi has to be periodic. So how do you solve this equation? This is, you just, as we said last week, you divide by phi squared, and you get an equation in 1 over phi, which is linear equation. So this is a simple equation like ordinary differential equation, right? You write u equals 1 divided by phi, u prime equals minus phi prime divided by phi squared. So if you divide this by phi squared, you get 1. Here you get 1 over phi, so it's u. And phi prime divided by phi squared, this is exactly u prime. So this is like an ordinary differential equation. You integrate, it has to be periodic, and you find that there is a solution. Okay, so now the question is, how do you solve an equation like this? So I have to give you also some limits. On the limit cycle Q0, which for zeta equals 0 and all S, by definition, since any of our eigenvalues has to satisfy 0 boundary conditions, so U and V, they have to be equal 0 on the limit cycle. So by definition, if you write it this way, because exponential is never be 0, K has to be 0. So this has to be equal to 0 for all S on the limit cycle. So this is one boundary condition. And when we go inside, so this is called really the inner solution, the boundary layer solution. This has to be equal. This has to go to 1. Why it's not written in my note? Okay, it's an important. But basically, the limit of Q0 of eta of S, not rho, but zeta, when zeta goes to so minus infinity, when you go back into the domain, this should be equal to 1. So now we have an equation. S is periodic. Zeta goes from 0 to minus infinity or plus infinity, depending if rho here, if we go, if n is this direction or that direction. So how do you solve an equation like this, which depend on two variables, zeta and S?
Can I interrupt? What is
Yeah.
this equation? Or why are we solving this?
This is what we've derived last week. I'm not going to redo it. This is what we derived last week. It's come from the transport equation. Okay. If we go to this, so here there's one equation we have solved. Here you go take this equation, take this function, plug it into this equation, and you found out that there is an equation to be solved. You change in this equation this, make this change of variable, and this equation can be, so there is a term in ds, the second derivative with s, which will goes to 0 because this is first order term, and you are left with this equation that has to be equal to 0 in order for this equation to be satisfied. Now the question is, how do you solve this? And what I'm saying is that this transport equation, so this is the case where there is no eigenvalue. When there is an eigenvalue, when we have an eigenvalue problem, which is this one, instead of, so if this is 0, you'll get 0. If you get minus lambda here, we'll have minus lambda Q0. So now it becomes an interesting question, how to solve this. If we can solve this equation, we may be able to get the lambda. All right, so how do we do this? So in general, suppose this is something in zeta squared, second derivative. There is a zeta here, which is like first order polynomial. And then the problem comes because here there is something that depends on s. Suppose this was constant for a second. If this was independent of s, then we get something that is depending on zeta, second derivative, the zeta, first derivative. Suppose it is independent of s, and then we get something that will only depend on zeta, something that only depends on s, and then we will do what is very classical, it's separation of variable. Find a solution on the form a function multiplied by a function of zeta multiplied by a function of s. Do separation of variable and see then if we use the boundary condition plus the fact that in s the function is periodic, that we can get exactly what we want for the lambdas. So the idea here is we're not looking at any variational, or because there is no approaches to get the eigenvalues. We just are analyzing how the solution of the Fokker-Planck equation or the eigenvalue behave in a small neighborhood of the limit cycle. And the limit cycle is exactly the obstruction to have a gradient. So we're going to get this information. We're going to capture this in this solution. All right, but we have not solved the question because it depends on s. So now how do we get rid of this dependency? Can we, by a magic change of variable, get rid of this term so that it becomes something independent of s? This is the trick. And this has been found 30 years ago, this type of trick. And the idea is to look for a function, look for a new maybe I'll continue here. The idea is to look, so we're going to make a change of variable, which is to write eta equals, so this is, we'll write it zeta of s, which is a function that I do not know. We will see how to find it. Multiply by the zeta. So we do a change of variable perpendicular to s. So at each direction which is perpendicular to the tangent of the limit cycle, we do this change of variable. And now we are going to derive a new equation. So let's write Q0 of zeta in S. This is a function, a new function Q0 of eta and S. Sorry, this is zeta, right? This is a zeta which is here. And so we have this, and now we're introducing a new function, xc to be found. All right, so which means that we have to find out an equation satisfied by Q tilde. So this is not very hard, just calculation. So let's do we are going to differentiate dq0 with respect to zeta. This is dq0 d eta d zeta. And d eta d zeta, this is simply psi of s dq0 d eta tilde. And I can do that twice. the second derivative, d dq0 d zeta squared is psi squared d dq d eta squared. And now we have to be careful at dq0 ds, because now the eta here contains s, so this is q0 of psi of s zeta s. So when we differentiate this with respect to s, we have to differentiate both the x variable and the y variable. So this is, if we differentiate this with the first variable, so this is zeta psi prime of s d q theta d eta, yeah, plus the second derivative with the first derivative of the second variable with respect to s. Okay, so I think we are good. Now we just have to take this into this equation. So the second derivative of zeta will give us xi squared of s d dq d eta squared. So I just replaced this by this plus minus. So what is zeta? Now, yeah, maybe we should do this calculation somewhere. Let's do it here. Zeta dq0 d zeta. So by definition, zeta is eta divided by psi of s. Eta divided by psi of s, and now we have to take dq0 d zeta, and this was calculated there. So this is exactly psi of s, which is here, dq0 tilde divided with respect, this is a derivative with respect to eta. So this and this goes away. So we are left with what? With minus eta dq0 tilde d eta, and multiply by what is left here, which is b0 plus 2 phi. 2 phi? Yes. And then minus b of s multiplied by this quantity, which is what? dq0 ds, dq0 ds, yeah, plus this term, and so this is now yeah, this is zeta. We have to write it in terms of eta minus or plus eta divided by psi of s multiplied by psi prime of s, and that's it, multiplied by, no, this is incorrect, multiplied by dq0 tilde d eta. And this doesn't change, equal to 0 or minus lambda. q0, nothing changes, I just make the change of variable here, so that I get this q0 of, so this is eta and s. So I have now same partial differential equation, except that I'm not going to divide everything by psi squared, and I'm going to position this, because this is the derivative with respect to eta, and this is the derivative with respect to eta. So I'm going to put this into this part. Right? So let's divide by what we want. So this is d dq d eta minus eta. So what do we get from here? d0 plus 2 phi. So I divide, so before dividing, minus b, eta is here, so I put it in here. Psi prime psi, and I divide everything by what I said, psi squared. Since I have a psi here, I multiply by psi, multiply by psi, remove the psi, and I'll do it cube. B dq, the eta squared, the eta, minus b of s, d dq ds, divided by psi squared, equals minus lambda psi of s is 0. So now we have to understand what have we win from this. So let's take, can I erase here? We are preparing a book to explain this new type of asymptotics. Okay, so now I have to remind you that phi was satisfying a Bernoulli equation. We said that phi squared plus b0 phi plus 1/2 of b of s phi prime equals 0. So now if we take psi equals square root of minus phi of x. Then psi satisfies the following equation. B of s psi prime plus b0 psi minus psi cube equals 0. Do you believe me? Or maybe we should do it. You just substitute. This phi satisfies this, then psi satisfies this. Right? Just substitution. You take phi squared, I mean, this is psi power 4th, then we have to differentiate this phi prime. So you'll get ultimately this equation. So phi is known, this is a non-function. What I'm saying is psi of s, what happens if we take psi, which is solution of this? What is b psi prime? This is the term here. Wait, I think we made a mistake. There is a minus here and a minus here. So this plus this, it should be a plus here, correct? Because minus and minus, so this is this. And I have added this term. So this is b psi prime. Psi b0, which is this term. Plus phi, are we correct? B0, yeah, B0 psi plus B and have a minus 2 psi okay, what can we say with this? Why are we missing here? Psi prime this. Yeah. So b psi prime, this is correct. Why do I get here 2 psi cube? B0 plus 2 phi plus b of s, B0 plus 2 phi, which is correct. plus this. So this is correct. Okay. Now b of s psi prime plus b0 psi minus this. Okay, so what? Okay, so phi by definition is psi. So let's write phi minus phi, this is psi squared. So I replace here minus psi, minus phi by minus psi squared. So this is exactly minus psi cubed. You agree? Now this equation, if I use this condition, we are left with what here? Here there is minus 2, and here there is minus 1. So I can write it this. I just put the 2 outside. So by definition, this is 0.
Okay.
And we are left with this psi cubed divided by psi cubed, which is equal to 1. So this disappeared totally. And this is can be replaced by exactly 1. And now this is great. Now this is an equation which is independent of s. I mean, it's a part of an equation, partial differential equation. So let me remove 1. So this is eta dq d eta. That's it. Minus this term equals this. Now this is now how do we conclude? How do we conclude all of this now? This is, how do we conclude now? Well, that's it. How do we solve an equation where all variables are not separated? If I use for the function q0 a function that we call, let's say, r eta t of s, then if we plug that into this equation, you do what we have learned at school. Just plug into here. What is the derivative with respect to s? This is nothing. So this is going to give us an equation, a second derivative equation for r. So this is r second minus eta r prime, right? Multiplied by t minus b of s psi of s d dq ds equals, so q of s multiplied by t, now multiplied by r, equals r t minus lambda psi of s. So this is so now we can, you know how you do that. You divide by r multiplied by t. So this is multiplied by r. You remove the t. This is divided by, so what is q here? This is q. This would be s. T goes away. We will divide by t. And here, this is you divide by r and t. So if this go this way, this should be a function of eta. This should be a function of s, and they have to be equal, which means that they have to be equal to a constant. And so we are left with, now this is not the achievement of all of this, is the two equations. So r second minus eta r prime. So let's write it a constant. So how do we call this constant? Call it lambda r. And then, this has to be equal to, we call it mu, I'm sorry. Let's call it mu. And then what we need is then, so this now is replaced by mu. And what we get is minus mu t plus b of s divided by psi of s dt ds equals minus lambda divided by psi s t. So we have two equations, 1 and 2. This is 1 and 2. All right, so this is actually very well-known quantities. This, the first equation, what is it? The solution of the second derivative. All right, we'll finish this. And then we'll make a break. So what is the solution of y second minus x y prime equals plus mu y equals 0? Those are called the Hermite polynomials, the Hermite functions. And actually this can be written r of eta equals exponential minus eta divided by 4. This is the Hermite polynomial of 2n plus 1, eta divided by square root of 2, and lambda and mu, and this is now the results, because to satisfy the condition that r of 0 has to be equal to 0 and at infinity r of 0, so there's two distinctions here. The limit of r eta when eta goes to infinity, this is 0. This is for the higher order eigenfunction. For the first one, the limit for r goes to infinity has to be equal to 1. So the first one, except the first one, where the solution is 2 eta q0 of eta and s equals square root, of 2 pi, 2 divided by pi, integral from 0 to eta of exponential minus z divided by 2 dz. So this is the case where mu is equal to 0. Otherwise, mu n is equal to 2n. So this will give us the first part of the eigenvalues. So we have solved here the first equation. This is the classical Hermite. And this is how it looks like. And eta, we said that eta here we had an equation for eta. This was this multiplication by xi. I think I've erased. Right, so eta, just to remind you what was the definition, eta was psi of s zeta. And zeta was the distance rho divided by square root epsilon. Okay, now how do we solve the second equation? The second equation is very easy. This is like a first order equation. This is a function t of s, multiplied by a function of s, dt ds equals a function in t. So this is like solving, it's an exponential. And now that we have to find out when the exponential has to be periodic, which will give us a condition on the lambda. Under which condition lambda, if if you integrate this, this will give you periodic boundary condition, I mean a periodic solution. So you can just integrate this. So this is exponential, you know, just we have a function, so I'll give you the result immediately. So T of S is equal to exponential of minus lambda of the integral from 0 to S of ds prime divided by B of S. So this is now the derivative, the field along the limit cycle, plus 2n. 2n is the mu. We have a mu here, but now we found what it is. This is the integral from 0 to S of psi of S prime divided by B of S prime ds prime. Now, when, I mean, what are the conditions for this function to be periodic? So, to be periodic, we start from a point, we go all the way, and we come back here. So, which means we have to look at the period of the limit cycle. Let's call it capital S. And the condition is that minus, when we come back here, the condition should be that this should be back to its initial value. So integral from 0, so I call capital S the period of the cycle. So this ds prime, I mean all of this function, plus 2n integration from 0 to S, psi of S divided by V of S prime, ds prime, has to be equal to, so if you have an exponential and comes back to the same, it means that this should be 2I pi m, but m is an integer. While here n goes only to positive integer. All right? So this gives us a condition on the lambda. So it's not that everything is complicated because we made it complicated. It's intrinsically complicated because the problem is not easy. And it comes in many places in physics and in chemical reactions. And when each time we will have a non-gradient field where we have the property that we have discussed here with the point close to the boundary, we need to calculate this eigenvalue where it comes from. Okay, so now we are done. Lambda nm. We can extract lambda from here. Just put this on this side and divide by this. So we can write it lambda nm, which is the this is a spectrum. It's n divided by pi, integral from 0 to s of psi of s divided by ds plus m I omega, where omega by definition is equal to 2 pi divided by the period, and t is the integral from 0 to the period of the cycle, ds prime divided by how the field, the vector field goes, the velocity of the field along the cycle. Right, that's the spectrum. So that's the spectrum for n. N is strictly positive, and m is in z. Here you can go to plus minus 1, plus minus 2, plus minus 3, and so on. So this is the spectrum. And for n and m equals 0, the first the first eigenvalue is calculated using a different, it's not the same form with the Hamid polynomial here, it's due to this erg function, the error function. So that's the spectrum. So the spectrum of the Fokker-Planck operator is lambda 0, the first eigenvalue that we discussed last week. And then you have to account for all of these lambda nm, which are obtained for epsilon small. This is the, and for n in here and m in z. Plus minus 1, plus minus 4. That's the spectrum of the non-selfadjoint operator. Okay, so this is, now what do we do with this? This is important because this explains to us the connection between, so we wrote the sum, I think it was before. We wrote the probability of exit point as a function of the sum of the exponential. But now this sum of exponential cannot be related to the precise property of the vector field. B, the interpretation of B is very easy because B of S is the velocity along the limit cycle. It's at the speed at which you are going to see you go around the limit cycle. Psi is a little bit more complicated because it's a solution of the Bernoulli equation, which depends on how B behave on the boundary, but also what happened at the velocity at which B evolved in the neighborhood, not just simply what happened on the limit cycle. So I'll finish with this application that we looked last week. I gave you an example of a limit cycle and a dynamical system for which we could get the critical point as close as we wish from this limit cycle. So you remember it was z dot equals b alpha of z, and this came because we conjugated the b alpha was the conjugation of b0 by the Mobius transformation, and b0 was the classical Hopf dynamical system, which was lambda z 1 minus z squared plus I, and let's call this omega tilde. But omega tilde is real, and lambda, there are two real. So here this is exactly, you have a dynamical system, everything is attracted at 0. And at 0, if you look at the speed, the derivative of I mean, if you look at the eigenvalue of the Jacobian, it's the imaginary part is exactly omega tilde. And so what we did last week is we used this and send this into this phase portrait by using conformal mapping, which is called Mobius transformation. Was psi alpha of z was something like z minus alpha divided by 1 minus alpha z. So the 0 here is sent at a point when z equals 0. This is 0, this is 0. So you're left with minus alpha. And so when alpha goes to 1, you can put your point as close as you wish from the boundary. And so we use this as an example of a class of dynamical system with a limit cycle and a point as close as we wish from the boundary. Okay, so now what is great here is we can look, and I'm not going to do all the calculations, we can look at how B0 look close to the limit cycle. because we have an explicit form. So it turned out, and so on this, I will refer to our publication. So I'll do this and then we'll stop for this and we'll make a break. And then we'll change completely subject after the break. So it turned out that capital B here equals to omega tilde, and B0 equals 2. So this is from the calculation by looking at the vector field. So B capital B, we have already discussed several times what it is, and B0, this is the other parameter when we expand. So this is the B here, and B0 is in here. B0 of S is equal to 2. I think we took for this the lambda. So let's take here lambda equals 1. And you can always all right. So now let's apply all what we have discussed here. If this is the case, then we have nothing to do basically. Just calculate an integral, which is what we have found here. Now, if B of S equals to a constant, integrating a constant, this is just a constant. So what we get in here, and the limit cycle is, the period of the limit cycle is 2 pi. You know, when we have a circle, you go and it's 2 pi. So we end up here having omega 2 so let's write the eigenvalues of the first one. Let's write the first eigenvalue omega 1 plus I omega 2. So not the first, but the second one who is not 0. Omega 1 here turned out to be equal to 4. And omega 2, which is just 2 pi divided by the integral of ds divided by B of S, which is what we have written so the real part, the imaginary part, I'm sorry, this is omega divided by pi. Yeah, 2 pi divided by t. T is 1 over this, so this is this. Integration from 0 to S. Correct? So this turned out to be exactly equals to omega tilde, which is this one here. Let's check the calculation. 2 pi. I think there is a 2 somewhere. 2 pi divided by t, this is 2 pi divided by t. If we multiply pi for n, there is a 2 somewhere, so that we get here this omega 2. There is something like incorrect here. N is not in front of everything. N because n and m are 2 independent variables. And here this is 1 over pi. And probably there is a factor 2 somewhere. So that when we are here, when we integrate 2 pi, is it correct? Oh, so I'm sorry. N, probably something like this. So when m equals 1, m equals 1, we get omega. Omega is 2 pi divided by t. T is this. So this is what we have written. Omega 2 is 2 pi, yeah, omega. So this is 2 pi divided by t, so this is this. So what does it mean? Now this is quite interesting because if we now look finally at the probability to escape, which is exponential, the first eigenvalue t plus exponential, so the constant c1, constant c2, exponential, so we get minus omega 1 t, cosine omega 2 t plus phi. So, what is the result? If you have the peak here, what gives you the period here of the peak is omega 2, which is equal to omega tilde, and omega tilde is exactly the velocity around this limit cycle, which is very surprising. It was completely unpredicted because all the process of escape has to do with the noise. The noise is driving the system outside.
Yeah.
But it turned out that only the deterministic properties are reflected here in this in the distance between the peaks, which is the omega 2, which is given by all of this. So this came really as a surprise. I mean, I don't understand why it's this, but I mean, this is what the math said, so there must be a reason. Okay, so I think I'm going to stop here. I'll give you the references. This is the hard asymptotics what we have developed over the past 5-6 years on this question to understand the origin of the peaks, to understand how they are connected to the intrinsic properties. And then we have used this to do a reverse engineering problem in neuroscience, which is basically if you have information about the peaks here that you can find in some problems, how can you reconstruct some information about the dynamics? And in neuronal networks, this is associated to the number of connections in neurons. Okay, so I give you a lot here, but I think if you're interested, the main ideas, which there are a lot in here, are there. So I'll give you references, and then we'll make a break of 10 minutes, and then I'll start the narrow escape problem, how long it takes for a Brownian particle to escape through a small hole. So all of this has been, so there is a first paper, which is myself and Schuss, and this is multi-scale modeling and simulation 2014. So you just go to my website or to Google or to Google Scholar. There is another one, which is Dowduke with a K, Schuss and myself. And again, it's going to appear soon in multi-scale modeling and simulation 2016, but it's on the archive. And then there is an application, and the application, I mean, again, all of these questions were motivated by dynamical system that has to do with neuroscience. It can probably appear in chemical reactions where you have all of these phenomena that we have described, all these conditions that are necessary. And then this was published in Frontiers in Computational Neuroscience. And again, this is the same author, Dowduke, myself, and others, and this was in 2015. And here in these Frontiers in Computational Neuroscience, we are giving the motivations. Any questions or?
It's really surprising because in the result, like the noise doesn't.
That's right.
But the whole thing is based on
Fokker-Planck equation.
Yeah.
That's right. But wait. I'm saying the peak. There are other properties that depends on epsilon. But I'm saying that because you look at the peak, just the position of the peak, and you can measure it, what I'm saying is that from the peak, this is what you can recover. There are other parts where it depends on epsilon, for example, or alpha. Alpha is the, the distance or the position of the. If the point is not, of course, close enough, you don't see the peaks. But the position of the peaks in this limit, when if the point is sufficiently close and epsilon is sufficiently small, these peaks are related to what happened near the speed at which trajectories are rotating around the limit cycle. The focus. Okay, so this is not what has been presented and what is known for stochastic resonance. Usually stochastic resonance, this is probably a special type of stochastic resonance, and probably all of this artillery that we have developed here can, or may be applied, we haven't tried it, to stochastic resonance. Okay, so let's break, let's take 10 minutes break, and then when we come back, we'll do, let's say, half an hour talk. I'll introduce a narrow escape problem. How long it takes for a Brownian particle to escape through a small hole. How long it takes for this to happen, what is the general methodology. So again, I'll start with the elementary question today and probably next week, and then we'll go to diastrate. Diastrate is what happened when you have to escape through a neck. And this is important for diffusion, because if you think about diffusion, when a particle has to squeeze between two obstacles, this is exactly going here through a narrow neck that has the shape of a cusp, especially when it's very narrow. All right, so we'll do this. So let's break. To see how it will affect the properties of the spectrum. Anyhow, this gives in general a methodology to study. I mean, you can think about extending all of the methodology we have here in dimension 3, or for more complicated situation where you have non-selfadjoint operator. I think there is no work on this. I mean, again, we did all of this because we were motivated by a question coming from neuroscience where we had exactly this situation to resolve. I mean, going for a pure speculative generalization is just part of pure mathematics. There is no clear motivation. You just do it for fun, for curiosity. Okay, so let's forget about all what we have discussed today. I mean, this is important. This is an application of this WKB. Now we switch gears and we go to the narrow escape theory. Okay, so this is going to take us this week and next week, and after we'll move on to really modeling in biology, data analysis. Probably I'll discuss super resolution data analysis.